Phase diagrams. So in a phase diagram, we're going to, it's like a map of the state or the phase. So phase and state just refer to which state of matter is it in, solid, liquid, gas. It's the state as a function of the pressure that's on the y-axis and the temperature on the x-axis. Here, it's going to look something like this. So we have regions. Here's the dark blue and the medium blue and the light blue. And then we also have lines or curves. This is a nice line, but these are curves. So the regions represent conditions where that state is stable. The lines or curves tell us temperatures and pressures where we're going to have an equilibrium. You'll have both states present, and they're named for the transition. So the vaporization curve is the transition between a liquid and the gas. A sublimation curve is between a solid and a gas, and the fusion curve is between a solid and a liquid. And those three curves typically intersect at a point, and three things intersecting at a point, we call that the triple point. That is a unique set of conditions where you can have all three states present at the same time. How does that work? I'm pretty sure I have a YouTube video for that. So here's a phase diagram for water. And the phase diagrams are going to look different for different substances. Even the slopes of the lines may change. And these are not drawn to scale. They're just, for a general understanding of what's going on. So here we have pressure. At 760 torr, that's 1 atmosphere of pressure, we know that water changes from a liquid to a gas at 100 degrees Celsius. And so this point is representing the vaporization of water at atmospheric pressure. If you increase the atmospheric pressure, if you use a pressure cooker, then the temperature at which that transition occurs goes up. If you decrease the pressure, then the temperature at which the water boils goes down. At atmospheric pressure and 0 degrees Celsius, right here, we have the transition between a solid and a liquid. We have melting. But you also, no, I'm sorry, that's at a different pressure. Never mind. Okay? So the pressure that you're interested in, the temperature that you're interested in, you draw straight lines, and where they intersect, that'll tell you what state that substance will be in at that temperature. Here's the critical point for water, way up here, and you get above that temperature, and you have a supercritical fluid. You do not have gas or liquid. You have supercritical fluid. Super means above, more. Questions?
Is that why the vaporization curve stops at that point?
Yeah, so the curve stops here because beyond that temperature, there's nothing that can boil. It's just both. I know that's hard to get your mind around. Yeah.
So what happens when you have like water and you microwave it that full,
Mm-hmm.
and it still looks like it's still in its liquid form?
Mm-hmm.
Move it in a second.
And they go, yeah.
Yeah, so it's like superheated?
Yeah, so you can get water superheated in the microwave, and you could try that at home, but be careful. So you heat the water up in such a way that it's not disturbed, and it can actually get above the boiling point, and then if it's jostled, disrupted at all, it begins to boil very quickly. And so you're like, the water's not boiling. Then you pull it out and it goes all over the place and burns your hand, right? That is more likely to happen if you boiled the water, you forgot to make the coffee or the tea. You come back later, it's like, oh shoot, and you boil it again. You've gotten all the dissolved air out of the water already, and so there aren't very good nucleation sites for those bubbles to form, and that's typically when you'll have that happen. Yeah. We talk about navigating within a phase diagram that's moving around, right? And so you could pick a pressure, so 1 atmosphere, and if we start down here, this is water again, and these are the same temperatures that we were using before. So at 1 atmosphere, at minus 25, water's a solid. As you go up in temperature, we get to the point where it melts, and now we're into, it's all melted and it's a liquid, and we continue to increase in temperature, we'll get to a point at which the water boils and turns into a gas. You can also look at a particular temperature and think about changing the pressure. So if we start here at room temperature and atmospheric pressure, and we cool it down. So it's still a liquid, we get to this pressure as we're cooling things down, and the ice will freeze at room temperature. That's kind of crazy to think about, right? You're like, what? You can also make it boil at room temperature. That's not freezing, that is boiling. What am I talking about? I don't even know what I'm talking about. Sorry. Reducing the pressure, we're not having it freeze, we're having it boil. Good grief. Hopefully tomorrow will go better. When we look at other substances, here we have iodine and carbon dioxide. The phase diagram can look quite different. So let's look first at this fusion curve. Here, this has a positive slope, and this one has a positive slope. Let's go back and look at the water. It's got a negative slope. Why? That's a good question. Because water is less dense as a solid. And so if you start right here, just above freezing temperature, and you go and decrease the pressure, the water will freeze. If you start down here, the water's frozen, and you increase the pressure, the water will melt. Do you want to know why ice is so slippery? Why ice skates work so well? When you put your weight on a thin metal blade of an ice skate, it puts a great deal of pressure on the water. And it actually causes the ice to melt very slightly, and that liquid water lubricates and makes it very, very slippery. You have a question?
What would it be that big of a difference from heavy water?
What about heavy water? Heavy water is water in which you have deuterium instead of hydrogen. My guess is that the phase diagram would be very similar, not a significant difference. Yeah. So these are more typical, where if you increase the pressure, you're going to cause it to condense or freeze into a solid. But water, as it freezes, it forms a more open structure and is less dense than the liquid water. That's why ice cubes float in water. That's not typical. Most things, the solid is more dense. It would sink in its liquid. The triple point for iodine is down here. Water has a triple point also. It's way down here at a very low pressure. Here's the critical point. This is carbon dioxide. And if you don't look at the scales here, you think, oh, well, that, it's not that different. But this critical point comes at 72.9 atmospheres and 31 degrees Celsius. That's a really high pressure, but a relatively low temperature. And that's why you can get supercritical CO2 and actually be able to use it. You don't have to go up to crazy high temperatures. For iodine to be supercritical fluid, you're going to have to go, up into the hundreds of degrees Celsius. That's not going to be an easy thing to do. But here's the triple point. It's at 5 atmospheres and minus 56.7 degrees. So down here at 1 atmosphere, you go across, and you got solid CO2, and it's sublime. So there's no liquid. There is no section of this that is a liquid at 1 atmosphere. That's unusual also. Iodine does have this small area here where it is a liquid at atmospheric pressure. Any questions? So you should be able to follow a line through a phase diagram and tell me what's happening. So here, following this line, from here, So we're starting at a point where the iodine would be boiling, going from a liquid to a gas, and as we increase the pressure, we've got a liquid, we continue to increase the pressure, it's going to freeze and become a solid, keeping the same temperature but increasing the pressure.